Good morning, everyone. My name is Dzung. I'm from the University of Massachusetts, Amherst, and I'm also very honored to be an NDSS Internet Society Fellow. In today's talk, I will be presenting our paper, RAIFLE, which is short for Reconstruction Attacks on Interaction-Based Federated Learning. Okay, so here's the motivation. So recommendation system and ranking system are probably one of the most widely used and most influential applications of machine learning. Every time you use a social network like Facebook, an e-commerce site like Amazon, an entertainment site like Netflix, a search engine like Google, you are interacting with a recommendation system, which are trained on massive amount of sensitive information data from users. And not only that, they are designed to encourage users to share even more information. And so it would be ideal if you have a privacy-preserving solution for this. Researchers have turned to federated learning as a promising direction to make this privacy-preserving. And as far as we know, we have not seen any real-world deployment of such systems yet, which is unfortunate. Nevertheless, it is very important that we anticipate and investigate any potential vulnerabilities that can arise from this particular setting. So, what is interaction-based federated learning? This is our generalization of the federated recommendation ranking settings. In typical traditional FL, the server do not have any control or influence over the user's private data. However, in IFL, the server actually can present items for the users to interact with. So let's look at some diagram. The server can prepare some items, which could be news recommendation, songs, product recommendation, search results. After preparing the items, the server can send them to the users so that they can interact with them. In our paper, we assume binary interactions, so click versus no click, upvote versus downvote, for example. So this interaction data is what the users want to keep private from the server. Using the items and the interaction data, the server can perform local FAR training, resulting in updated model, which is then aggregated by the server to produce better models. So the question now is, what kind of harm can the server causes to the user? In the honest but curious setting, the server can perform a classic or a very well-known attack called gradient inversion, where they simulate the user's local training in order to try to guess the interaction via optimization. To defend against this, popular methods include applying differential privacy and also incorporating secure aggregation to break up the link between the update and the user's identities. So we evaluate vanilla gradient inversion on two recommendation datasets called MovieLens and Steam. We target a specific learning algorithm called Federated Neural Collaborative Filtering. For our baseline, we use an attack that was published in WWW 2023. It is basically a random discrete search that doesn't make any use of optimization. And vanilla gradient inversion can outperform this IMIA attack significantly, achieving more than 0.9 F1 score in both datasets. Even when using the defense proposed by the baseline, vanilla gradient inversion can still outperform non-trivially. So that is the honest but curious setting. What about what if the server is malicious? What kind of harm can they do? What kind of malicious activities can they perform to improve the reconstruction rate? So researchers have looked at manipulating the model weights, and there have been quite a few works on this problem, and they've shown that manipulating model weight is effective. However, it usually makes certain assumptions about the models. For example, the model architecture has to be usually like CNN, for example. But in recommendation ranking, sometimes the learner, the ranker, is simply a linear model or just a small neural net. So what can we do? Can we exploit the control of the server over the presented items in order to improve the attack performance? And this property is unique to interaction-based federated learning and has not been explored before. So our attack idea is as follows. can we modify the features or the representation of the item in such a way that their contribution to the gradient, the model update is as unique as possible, as discernible as possible for the reconstruction. And one strategy is you can assign a unique subset of features to each item so that each of the item will uniquely influence just these particular parameters. So here's an example where you have 3 items. You have each item has 3 features, so you assign 1 feature to each item, and all the other features have 0 values. In this way, we find that it can work, but one big drawback is it's very obvious. You can see a bunch of holes in the data. You just detect all the zeros, and from our experiments, it did not really scale well when there are many items, especially when the number of items are larger than the number of model parameters or features. Another approach that we found is it's also very simple. We simply replace the feature values, inject random noise into the feature value, and this essentially achieves the purpose of trying to unify the contribution of each item. And if we find that it can meta scale to the number of items. So for the evaluation, we tested on 2 learning to rank datasets called MQ and NSLR collected by Microsoft. And we target a federated algorithm called Federated Pairwise Differentiable Gradient Descent. And our baseline is just regular vanilla gradient inversion. And we use AUC, area under the ROC curve, as the metric. And these are the numbers. There are a lot of numbers, but the key takeaway is our RAIFLE attack consistently outperform vanilla gradient inversion across all of the settings that we have tested. And it especially can scale as well when the number of items increase. Yeah, so before we move on, I get this question a lot during review and during discussion with other people. Is this Pham model too strong? Is the ability to modify features however you want too unrealistic? And I want to convince you that this is not the case at all. With 3 historical examples. In 2014, Facebook was manipulating the newsfeed of nearly 700,000 users for the purpose of an academic study called emotion contagion, which I guess is how users' emotion is affected. In 2021, Amazon was caught and fined for manipulating their product recommendation results. And very recently, Google was fined more than 2 billion euros for manipulating their search results. So these examples highlight the practicality of our Pham model and just showcase how these big tech companies, the amount of influence these big tech companies can have. Okay, so what if the server cannot directly control the training features? Here's an example, image ranking. So the server sends some images to the users. The users use some pre-trained computer vision model as the feature extractor. So in this case, the user is doing this locally, and the server cannot directly change the extracted features values. So what we want is a way somehow for the server to be able to modify the image so that we can still benefit from the noise injection method. Can we make the extracted features resemble noise as much as possible? And so the answer is, well, optimization again, but there's a trick. Starting from an initial image, you run it through the feature extractor, you get a feature vector, and what you can do is you initialize some random noise for the feature vector, and then you minimize the loss between the extracted and the random noise target, optimize it with respect to the initial image. However, we find that if the dimension of the feature vector is too large, let's say, not too large, but like 1,000 features or 2,000 features, for example, then this optimization doesn't work very well. It cannot make the extracted features resemble noise at all. And our trick is to partition the noise vector, the target noise vector, into so that we have multiple targets, noise vector targets. Each target has a subset that is that has Gaussian noise and the rest is zeros. In this case, we have 2 targets, and we perform the optimization as usual, resulting in 2 different variations of the manipulated images. And when the server has to send the images to the users, they can choose either one of these randomly and send that to the users. Here are some examples of the manipulated images. I'm not sure if you can see this from your point of view, but if you squint really hard, you can see that the manipulation has some very small, slight discoloration, which is not very noticeable, but is there. This showcases, I guess, the stealthiness of the manipulation. And we evaluated this using the ImageNet dataset with 4 different feature extractor, ResNet, DenseNet, and so on. We compare to vanilla gradient inversion and also an adversarial attack method called fast gradient side method, a very classic gradient attack, adversarial attack, using AUC metrics. And across many of our settings, our attack can consistently outperform the other 2. And they also scale very well when the number of images increase relative to the number of dimension of the feature vectors. So we tested some defenses against our attack. Local differential privacy works obviously very well as expected, but we find that RAIFLE can squeeze, in some scenarios, RAIFLE can squeeze as much reconstruction performance as possible, more than just regular gradient inversion. And typically people combine local differential privacy with secure aggregation. In our case, in order to make our attack work with secure aggregation, we have to modify the attack a bit so that we have to target a small subset of users. Here's an example. We like the fingerprinting approach. We partition a certain subset of the feature space to a particular target user, UK, and we find that our attack can still be effective for a number of participants in the 100 branches, and I guess small enough local differential privacy noise. Some other defenses could be checking for manipulation, minimizing shared information, and perhaps changing the FL architecture. So to conclude, we introduce a novel attack that is unique to the interaction-based varied learning. Possible improvements could be making it more stealthy, extending into other domains, and perhaps combining it with model of manipulation. Our code is available publicly on GitHub, and thank you for listening, and I'm happy to take any questions.
So we have time for one question. Are there any questions from the audience? Yeah. Maybe if it's quick.
Thanks for your presentation. So my question is quite straightforward. It's about when you send the picture, because you need to manipulate the image, right? So you need to depend on the feature extractor. So is that feature extractor, do you need a surrogate model for the feature extractor? Suppose the client has a different feature extractor.
So in our setting, we assume that the server knows the feature extractor. We haven't. I think that is so the server needs to know the feature extractor so that it can perform the ranking in order to send the ranked images to the server. So if you use a different feature extractor, then it's not going to work with the ranking, essentially.
All right, let's thank the speaker. There is a question. Please follow up offline here.
Okay.
No? Thank you.